So, we will continue in this session with solving thermodynamics problems. Yeah, it is an easy problem, let us solve it. Molar density of water vapor. Molar density of water vapor in mole per meter cube is 33, right, of water vapor. The compressibility factor under this condition at a normal, so water vapor at normal boiling point. The compressibility factor under this condition is close to which one of the following? So, basically it is PV equal to ZRT for 1 mole. So, Z you see it is PV by RT. Now, P equal to 101.325 kilopascal, normal boiling point 3 is 373 Kelvin, right, and V is given as 1 divided by rho, so which is 1 divided by 33 meter cube per mole. So, if I substitute the values, I can get an approximate Z. Okay. Right. So, another question, it is again related to partial molar property. The partial molar volume of water in its mixture with methanol, water 1, methanol 2 at 25 degrees Celsius and 1 atmospheric pressure can be approximated as V1 bar equal to 18.1 plus or minus 3.2 x2 square. Develop an expression for the partial molar volume of methanol, this for water, partial molar volume of ethanol at the same condition, right. We have to generate the expression. This should be some function of x1 or x2, right, whereas pure volume of methanol is 40.7 centimeter cube per mole, right. So, basically you see here we have to use Gibbs duhem. Okay. So, x1 dV1 bar plus x2 dV2 bar equal to 0. So, x1 dV1 bar equal to minus 3.2 into 2 into x2 plus x2 into dV2 bar into dx2 obviously. Here we will have, we are taking the derivative or differential rather. So, it will be dx2 plus x2 into dV2 bar equal to 0, and from there we have to integrate, okay, and replacing x1 by 1 minus x2. So, we have a division and therefrom we can integrate. Now once we integrate, V2 will be a function of x2 plus a constant. Now we have a pure species volume given, which is to be used as boundary condition for this function to solve for C. That means x2 is equal to 1, V2 bar equal to V2, and if I substituted that over there, we will get the V2 bar expression. It's quite simple. And similar this partial molar property based problems we have in gamma also, where we have to use this Gibbs to M equation. See this, we have this x1 d ln gamma 1 plus x2 d ln gamma 2 equal to 0. Say gamma 1 is given to you, right, and you are asked to solve for gamma 2. So what you will do? Gamma 1 expression, you take the differential, substitute, and we know that x2 is equal to 1, gamma 2 equal to 1, which will not be supplied unlike the previous case, because it is a universal boundary condition for activity coefficient, and from there we can solve this gamma 2. Okay. So, this is also a gate problem. I forgot the year exactly, a 2 marks gate problem. Consider a binary mixture of MEK and toluene, methyl ethyl ketone component 1 and toluene component 2 at C23 Kelvin, right. The activity coefficient gamma 1 and gamma 2 are given as ln gamma 1 is equal to x2 square xi 1 minus xi 2 plus 4 xi 2 x1, and ln gamma 2 square gamma 2 is equal to x1 square xi 1 plus xi 2 minus 4 xi 2 x2. Where x1, x2 are mole fractions in the liquid mixture, and xi1 and xi2 are parameters independent of composition. At the same temperature, the infinite dilution activity coefficients are given by, we have ln gamma 1 infinity 0.4, ln gamma 2 infinity 0.6, sorry 0.2. The vapor pressure of MEK and toluene at 323, that is P1 sat is given as 36.9 kilopascal, P2 sat is 12.3 kilopascal. Assuming the vapor phase is ideal, the equilibrium pressure of the liquid mixture containing 90 mole% of the toluene. So, P we have to solve, it's given x2 is 0.9, so x1 equal to 0.1, right. So, it is a bubble P problem, and we have to basically solve for gamma 1 and gamma 2 at this specific composition, but we have to know xi 1 and xi 2. For that, we will use these two values. See, ln gamma 1 infinity is equal to limit x1 tending to 0 ln gamma 1. So, when x1 is equal to 0, this part vanishes and x2 is equal to 1. So, it is xi 1 minus xi 2, which is 0.4, right. And ln gamma 2 infinity, its limit x2 tending to 0 ln gamma 2, right, x2 tending to 0. So, this part vanishes, x1 equal to 1, and we have gamma 1 plus gamma 2, sorry, xi 1 plus xi 2 equal to 0.2. So, if we simply add 2 xi 1 equal to 0.6, so xi 1 equal to 0.3, right, yeah, xi 1 minus xi 2. So, if I add, so this cancels out, so xi 1 and xi 2, that is 0.2 and this is 0.3, and if I substitute 0.3 here, so xi 2 equal to minus 0.1, right. So, we have now the foolproof expressions of gamma 1 and gamma 2 for that specific temperature, and next we have to solve for P, and P is equal to x1 gamma 1 P1 sat plus x2 gamma 2 P2 sat for modified Raoult's law, which considers the vapor phase to be ideal. So, P it's equal to x1 is 0.1, gamma 1 at 0.1 into P1 sat, it's 36.9. We will keeping it in kilopascal, so P will be in kilopascal, and this is 0.9 into gamma 2 at 0.1, gamma 2 at x1 equal to x1 equal to 0.1. Here also I should write x1 equal to 0.1 and P2 sat, that is 12.3. So, I will get P in kilopascal, right. So, idea is here to relate the temperature dependent parameters of activity coefficient model to these infinite dilution property or infinite dilution activity coefficients. So, from there we can solve this, and rest is pretty simple. There are some VLE problems as well, but this is also a VLE problem basically, but most of the problems are based on this Raoult's law. We can easily solve it. I am not going into the detail. If I find something interesting, definitely I will solve it. See another, the saturation pressure of water at 180 degree P sat water, it is given 1.0027 megapascal, right. Critical constants of waters are Tc equal to 647.3 Kelvin, Pc is equal to 221.2 bar. Calculate the eccentric factor. So, just eccentric factor, you see it is defined as minus 1 minus log to the base 10 PR sat at TR equal to 0.7. So, we have to check 180 degree whether it corresponds to TR equal to 0.7. Definitely it must correspond. So, TR is T divided by TC, 273 plus this 180 divided by the 647.3 Kelvin. Definitely I am 100% sure that this will be giving you 0.7. So, here PR sat equal to P sat at TR equal to 0.7 divided by PC. So, this 1.0027 into 10 to the power 6 divided by 221.2 into 10 to the power 5, right. So, find out this PR sat at TR equal to 0.7, at TR equal to 0.7, substitute that expression here, so we will get the eccentric factor. So it's 2004 2 marks problem. A vapor pressure of water is given by ln Psat equal to A minus 5000 divided by T, where A is a constant, Psat is a vapor pressure in atmosphere, this Psat is in atmosphere, right, and T is in Kelvin, right. A value is not given. So we have to find out the vapor pressure at T equal to, it's 50 degrees Celsius, so this 23 Kelvin. What is that? So basically the problem reduces to that you have to find the value of A, but we have to note that this is water, and for water Psat is equal to 1 atmosphere for T is equal to 373 Kelvin, because it's the boiling point, right. So this data is to be used to calculate A. So ln of 1, which is 0, equal to A minus 5000 divided by 373. So A will be 5000 divided by 373. So rest you substitute the value of A and get the answer. So another problem, this is 2015 2 marks problem. (2015) 2 marks problem. See, GR and VR are related. It's given that GR by RT equal to 0 to P VR by RT dP, right. Find GR at T equal to 300 Kelvin and P is equal to 0.2 megapascal. What is given? The gas may be assumed to follow virial equation truncated after 2 terms, Z equal to 1 plus Bp by RT, and B value is given as minus of 10 to the power minus 4 meter cube per mole. Okay. So to find out GR in joule per mole. So what we have to do? See, VR is V minus VIG. So ZRT by P minus RT by P. So it is Z minus 1 RT by P. So VR by RT equal to Z minus 1 by P. So it's very obvious because this is equal to the pure species fugacity. So ZR by RT equal to 0 to P Z minus 1 dP by P Z minus 1 ln P. Oh sorry, Z minus, sorry. So Z minus 1 is Bp by RT dP by P, 0 to P, Pp cancels out, so Bp by RT. So that is GR by RT. So GR is equal to B into P. So B is minus of 10 to the power 5, 10 to the power 4 meter cube per mole multiplied by P. P is 0.2 into 10 to the power 6 Pascal. So from there I will get joule per mole. Why? Let's check. Meter cube per mole and this is Pascal, which is Newton per meter square. So Newton into meter per mole, which is joule per mole. So you are getting this GR as B into P. This GATE 2015 2 marks problem. Okay, let us solve this. It is not a GATE problem. Ethanol and benzene. Ethanol 1, benzene 2. Ethanol and benzene system forms an azeotrope with 44.8 mole percent of ethanol. Azeotrope at x1 equal to 0.448. Ethanol with a boiling point, 44 with a boiling point of 68.24 degrees Celsius and pressure equal to 760 torr. Note that azeotrope has got a unique boiling point because no matter whether it is maximum or minimum boiling azeotrope, for max this will be, and for minimum, so we have a unique boiling point. So this is T versus x1, this is T versus x1. This is T1 sat, this is T2 sat, here T1 sat, T2 sat. Right. The saturation pressure of ethanol and benzene at the same temperature, 68.24. So P1 sat equal to 506 torr. Torr is millimeter of Hg, and P2 sat is equal to 517 torr. What is the question? Estimate the Van Laar constant of the system and evaluate the activity coefficient for a solution containing 10 mole percent ethanol, A and B, and activity coefficient gamma where ethanol is 10. So you see that the pressure is given and we have to use this, we have to get this gamma 1 and gamma 2, right. So at this P is equal to x1 gamma 1 P1 sat plus x2 gamma 2 P2 sat. That is a general relation. And P is 760 torr, that is 1 atmospheric, 0.448 into gamma 1 into P1 sat, that is 506, plus x2 1 minus 0.448 into gamma 2 into 517. So we'll get some x1 plus some constant into x1 plus some another constant into x2 equal to a constant. So it's a linear addition wise equation. And for azeotrope, x1 gamma 1 p1 sat equal to gamma 2 p2 sat. So gamma 1 by gamma 2 p2 sat, that is 517, divided by p1 sat, that is 506. So from these two we can solve for gamma 1 and gamma 2 at x1 is equal to 0.448 and at that specific temperature and pressure. Now Ge by RT is equal to or what is van Laar? x1 x2 divided by Ge by RT is equal to B by x1 plus A by x2. Right. So from there we get that Ge by RT is equal to A x1 x2 A by B x1 plus x2. Right. No, it's a linear function. So I've done a mistake. X1 by B plus x2 by A. So A, if I multiply here, it's A by B x1 plus x2, and this is the theory, right? And that's equal to x1 ln gamma 1 plus x2 ln gamma 2 from summability. So you get this expression, right? So you get this expression, we get a relation between A and B, and other one is to be obtained, that's G by RT or ln gamma 1 ln gamma 2 expressions actually we have to solve. I don't remember this, and don't worry, it's not a gate problem. Basically it is ln gamma 1, it's equal to A divided by 1 plus A by B x1 by x2 whole square, and ln gamma 2 is equal to B divided by 1 plus A by B 1 plus B by A x2 by x1 1 plus B by A x2 by x1 whole square. You don't have to remember this equation. So let's drop this, and we can use this ln gamma 1 and ln gamma 2 to solve for A and B from these two equations. And once these are known, we can solve for A and B, and next again upon substitution of x1 equal to 0.1 and x2 equal to 0.9, we can solve for gamma 1. So from here we can solve this A and B, and once we know this A and B, the first part is obtained, and second, in this expression A and B we will substitute x1 equal to 0.1 and x2 equal to 0.9. So you can solve for ln gamma. So next, okay, let's solve another type of problem. This is not a gate problem. Saturated water at 300 degree Celsius has a vapor pressure Psat as 8592.7 kilopascal, and fugacity, the saturation fugacity is 6738.9 kilopascal. Under this condition, 1 mole of water in liquid phase has a volume. So, liquid has got a volume as 25.28 centimeter cube per mole, and vapor phase volume is 391.1 centimeter cube per mole. What is the fugacity of water? F at pressure is equal to 9000 kilopascal. Okay. So, it is pretty obvious that we have to use the concept of Poynting factor, which states that F compressed liquid, F saturation equal to exponential of VL P minus Psat by RT, right. So, F compressed, what is the pressure here? 9000 kilopascal is equal to F saturated, which is 6738.9 kilopascal into this exponential factor. Now, VL, this is also the molar volume, is 25.28 centimeter cube. So, it is 10 to the power minus 6 meter cube, right, 10 to the power minus 2 and 10 to the power minus 6 meter cube per mole, multiplied by P minus Psat. P minus Psat equal to, so into 9000 minus 8592.7 into 10 to the power 3 Pascal divided by RT. R is 8.314 joule per mole per Kelvin into temperature 300. So, this is 273 plus 300, 573. So, see, this part is dimensionless because meter cube per mole into Pascal, Pascal is Newton per meter square. So, you solved it. So, it is joule per mole, and here also it is joule per mole. So, you multiply, so you will get the answer. Find the exponential factor and multiply, so you will get the answer. Okay? The heat of fusion of ice, delta H, fusion we will write SL of ice. Heat of fusion for ice is 80 calorie per gram, that we all know. At 0 degree and at 0 degree Celsius, 1 atmospheric pressure, right. The ratio of specific volume of ice and water is V ice, V water is 1.091, and specific volume of saturated liquid water 0.001 meter cube per kg. So, what we have to estimate? dt dp sat. Basically, here we have to use Clapeyron equation, simple application of Clapeyron equation, which states that dp sat dt equal to delta H SL divided by T into delta VSL. So, as this will be T or Tsat is 273 into delta VSL, which will be VL minus VV, right, VL minus VV, because the final state is liquid, the initial state is solid, and divided by delta H SL. So, it is 273 into this is water is given. So, VL, if you consider 1 minus Vs by VL divided by delta HSL. So, you substitute the ice to water volume, it is higher, so it will be negative, right. So, it will be giving you negative. So, answer is 273 into VL 0.001 meter cube per kg. Always write the unit, it is in Kelvin, and this is obviously 1 minus 1.091, that divided by delta HSL, which is 80 calorie so per gram. So, we can convert it. So, 80 into 4.2 joule per gram into 10 to the power 3 gram per kg, right. So, it is joule per kg. So, 80 into 4.2 into 10 to the power 3 joule per kg. So, here it will be 80 into 4.2 into 10 to the power 3 joule per kg. So, it is dt dp sat, right. Whether it is exactly coming. So, we have kg cancelling out, joule, see, Kelvin you keep it. So, kg cancelling out, joule is basically joule per meter cube, right. So, Newton per meter divided by meter cube, so it is Pascal. So, the answer will be in Kelvin per Pascal. So, here we have to use Clapeyron equation and not the Clausius-Clapeyron. Clausius-Clapeyron is only valid for liquid to vapor or the vaporization curve. It gives the saturation pressure temperature relation for vaporization, or rather this liquid vapor equilibrium or boiling. Okay. Determine the boiling point of water at a pressure of P is equal to 2 atmosphere. We have to calculate TBP. Water, for water. Water, given the boiling point at 1 atmosphere. So, we know this Psat is 1 atmosphere at TBP 100 degree Celsius, right, and enthalpy of vaporization is essentially constant. So, we have to use Clausius-Clapeyron. LV is 2257 kilojoule per kg. So, you have to calculate the boiling point at 2 atmospheric pressure. So, you see what is Clausius-Clapeyron? dP sat dt equal to delta H LV R delta V LV. So, delta H LV by R. In case of any confusion, derive this. So, this is VV because VL is negligibly small, that is the assumption, and delta H LV divided by R. VB is equal to this, no R, it was T. So, this is T and RT by Psat. So, d ln Psat d of 1 by T equal to minus of delta H LV by R. Right. So, we can write ln of P2 sat by P1 sat delta H LV by R 1 by T1 minus 1 by T2. So, we have to calculate this boiling point. So, 2 by 1, so ln 2. Now, delta H LV is 2257 into 10 to the power 3 joule per kg, right? And here in the denominator 8.314 joule per mole per Kelvin. So, mole you convert to kg. So, 1 mole 18 gram and 10 to the power 3 gram 1 kg. So, it has been converted, and 1 by T1, originally T1 is 100. So, it is 373 minus 1 by T2. So, we will be getting T2 in Kelvin, right. So, you see that here is the point that we commit majorly the silly mistake, because this is in per mole unit, this is in per kg unit. Okay. Water at 45 degree and 10 kilopascal. 45 degrees Celsius and 10 kilopascal. Water enters an adiabatic pump and is discharged at a pressure of 8600 kilopascal. Pump efficiency is 75%. Right. Calculate the work done by the pump, temperature change of water and entropy change of water. So, work done by pump, find. This is not a gate problem. So, work done by the pump, temperature change and entropy change. This we have to calculate. Now, given that for saturated liquid water at 45 degree, saturated water at 45 degree, V is equal to 1010 centimeter cube per kg, beta is equal to 1 by V, that is del V del T, volume expansion coefficient 4.25 into 10 to the power minus 4 Kelvin inverse, Cp is equal to 4.178 kilojoule per kg Kelvin. Right. So, basically we have to get the equations for delta H and delta S, right. And this efficiency is not the typical pump efficiency we have studied in fluid mechanics, it is with respect to isentropic process. Okay. So, if it is an isentropic process, here you see the temperature finally its pressure is given. So, what we know? We know P1, let mark it as 0.1 and this is at 0.2. So, P1 is equal to 10 kilopascal, T1 is equal to 273 plus 45. So, it is 318 Kelvin, right, and P2 equal to 8600 kilopascal, and efficiency is 75%. So, ds equal to Cp, I do not know any formula right now. So, we will derive Cp dln T, that is Cp dln T plus del S del P at constant T dP. The basic property relation we are using here. So, you see that this we have to solve, and we know that TdS del S del P we have to replace, right. So, here we have to use the appropriate this Maxwell relation. So, minus of S dt minus of and plus of VdP, right, that is dg, and this g being an exact derivative, it will satisfy this del S del P at constant T equal to minus of del V del T at constant T. So, ds is equal to Cp d ln T minus del V del T at constant P dP, right. So, Cp d ln T minus this is beta into V dP, that is ds. So, delta S is equal to Cp ln T2 by T1 minus beta, liquid volume is nearly constant, into delta P. Okay. So, first we will consider isentropic process, right. So, isentropic process means delta is equal to 0. So, Cp you see is 4.178 into 10 to the power 3 joule per kg per Kelvin into ln of T2 by T1 minus beta, convert everything to this SI units, 4.25 into 10 to the power minus 1 is Kelvin inverse into VL. V is centimeter cube per kg. So, we have to convert it to meter cube, 1010 into 10 to the power minus 6 meter cube per kg into delta P. So, 8600 minus 10. So, 8500 into 10 to the power 3 Pascal. So, from there this set equal to 0. So, from there get the value of T2 isen, right. So, T2 isentropic we have calculated first. So, once T2 isentropic is solved, next you see this minus of Ws is equal to delta H, right. So, Ws is equal to in joule per kg, and this is also the specific enthalpy. So, delta H, what will be that value? What will be that value? So, that is to be considered here, the delta H expression. So, dH is equal to, you see, Cp dt plus del H del P at constant T dP, right. I am not using the final formula. So, dH from the second fundamental relation TdS plus VdP. So, del H del P at constant T is equal to del S del P at constant T plus V. Now del S del P at constant T is minus del V del T. So V minus beta V, and there will be a T of course. So beta Vt. So dH is equal to Cp dt minus this 1 minus, or sorry, this is plus plus. So V minus beta Vt. So V into 1 minus beta T. Right. So delta H is equal to Cp delta T minus VL. This is dP. This is dP. So VL 1 minus beta T into delta P. So that's the final expression of delta H. Correct. So once you see we get this T2 Eisen. So delta H Eisen is equal to Cp T2 Eisen minus T1 minus VL. I am not going for exact calculation. This T2 beta into T into this delta P. Right. So this T we can take this mean, arithmetic mean, or let's say we can, as the temperature change in a pump is very small, this will be T1, right. So I will get delta H Eisen. Now minus of Ws is equal to delta H, and minus of Ws Eisen equal to delta H as well, delta H Eisen, right. So eta, see, it's a work consuming process. So this eta WH delta H Eisen will be always lower than delta H. So eta is equal to delta H Eisen divided by delta H. So we have solved for delta H Eisen. So delta H is delta H Eisen by eta. So delta H Eisen by eta we have solved, and again we will use the same formula that delta H is equal to Cp next T2 minus T1 minus VL minus, or this is minus or plus, this will be plus, right, this will be plus, yeah, this will be plus. So plus VL into 1 minus beta T, 1 minus beta T into delta P. Now you know this is T1, you know that, this VL you know, delta H you have calculated, solve for T1, so T2, the outlet temperature. So my first, this delta T2 is solved, and once delta T2 is solved, again we these of delta H, and from their Ws we have already solved it, and delta S, again put back the formula here, so you can calculate delta S. So it's a complicated but conceptual problem, by which this is not at all a gate type problem, but it's a general problem by which we can actually calculate the entropy change, temperature change, and work done by a pump given we know this isentropic efficiency. In a closed piston cylinder system, we have a piston cylinder system, we have methane, right, which obeys the gas equation P within bracket V minus NB is equal to nRT, right, where B is equal to, only volume correction is made, B is equal to 0.029 meter cube per mole. The temperature and volume, T1 temperature, it's 500, so 273 plus 500, 773 Kelvin, and pressure, volume is 5 meter cube, right. At this state of the system, and it's 100 moles of methane. This 2018 GATE problem of 2 marks. At this state of this system, the isobaric rate of change of temperature with volume. So, del T, del V with P. What is that? So, you see here pressure remains constant, so you have to take the derivative with respect to volume, right? N is fixed. So, if I take the derivative, P V minus N B is equal to nRT. So, you will be going to take this with volume. So, P V minus N P B is equal to nRT. So, P into del V, P into P only, because we are taking the derivative. Here it's 0 because there is no volume term. nR del T del V at constant P. So, del T del V at constant P is equal to P divided by nR. So, pressure, it is not given. So, we have to use this P is equal to nRT divided by V minus NB. So, P is equal to nRT, nR, V minus NB. So, nR cancels out, T divided by V minus NB. So, temperature is 773, volume is 5 meter cube minus 100 moles into B, B is meter cube, so 0.029. So, that in Kelvin per meter cube will be the answer. Okay. So, here we close this session, and in the next session we will be solving the problems of this general SFE, entropy, first law, second law type problems, which were given in GATE, and also for some general problem that we are going to solve in the next session.